Okay, so we are starting the IS number 23 notes on analysis of variance, which is abbreviated ANOVA. So part 1 is about movies. We have a couple of big ideas. And again, this is section 11-4 if you want to look at it in the textbook. So ANOVA is a method of testing the equality of three or more population means. So back in section 9-3 and 9-4, we talked about the difference of two independent sample means, or the difference between matched or paired data between two samples. So now we're talking about three different samples coming from three different populations that we want to test their means. So one other thing that we need to know when we're talking about ANOVA is that a treatment or factor is a property or characteristic that allows us to distinguish one population from another. Okay, so when we go to look at our data, we want to make sure that each sample is only separated by one treatment. There's only one thing that is separating these out. Okay, so at recent showings of these three movies, Frozen 2, Avengers Endgame, and Knives Out, random samples of 5 people, it is important that they're random samples. There are conditions to discuss here. I'm not going to discuss them fully this time. You can look them up in your book, but of course we want random samples if we're taking samples. So random samples of 5 people were selected and their ages were recorded. So the results are as follows. Okay, so just as I'm scanning the data, looks like the Frozen 2, as anticipated, has quite a few young people there. And I'm thinking maybe this is a parent. And then Avengers Endgame has fairly young adults, right? And Knives Out looks like it's got some older adults, which kind of makes sense. Each of these movies were kind of geared toward certain categories of people. Okay, so what we want to know are the differences that I'm seeing, is that enough information to actually say that there's a true difference in the population of people who go and watch those movies, not just the sample effect people? So the treatment or the factor, which again is the property or characteristic that distinguishes these populations. So really we're talking about a population of moviegoers. Is it the same for all three of these movies, or does the movie they're watching distinguish them? So the treatment or the factor is the movie. Okay, or I should say the movies. It is the characteristic that we're using to separate our data into groups. All right, so now suppose we wish to compare the three mean ages in order to see if there's any significant difference. I can tell there are some differences, but I want to know if that's significant between the three, again, it's important that there are 3 or more, mean ages of people attending these 3 movies. Okay, so then our hypotheses here would be that mu1, let's assume that this is sample 1, and then this Avengers Endgame is sample 2, and Knives Out is sample 3. Each of those is going to be 5, I think, right? So our hypotheses would be mu1 is equal to mu2 is equal to mu3. And again, I'm just listing 1, 2, 3. The alternative hypothesis would be that those means are not equal. I can't say that they're not equal by any certain amount, or that one is different from the others and 2 of them are the same. I just have to say that in general, they're not equal. Okay, so again, usually in this case, our claim is that they are, or we want to see if they are different, but sometimes we want to see if they are the same. Regardless of what the claim is, the null hypothesis is always where we put the equalities, and the alternative hypothesis is always where we put the inequalities, where something is not equal, greater than, less than, something like that. Okay, so in order to proceed, we have to compute some information from our table above. So we need to know the sample size for each of them, the sample mean for each of them, and the sample standard deviation for each of them. Ooh, except that's not just S1, S2, S3, it's S1 squared. So this is the variance for the first sample, right? Remember, standard deviation is equal to the square root of the variance. And we can reverse that equation by saying that the variance, or, well, I guess I'm not even going to write it that way. If we square both sides here, we get S squared. The variance is S squared. That's the notation that we often use. So this is the sample variance, not actually the sample standard deviation. We'll have to be careful when we look at the descriptive statistics for that. Okay, so I could have just given that to you, but I did want to show you how to calculate descriptive statistics in StatDisk. So what I've done is enter each of these 3 columns into StatDisk. So you probably want to pause the video and go ahead and enter your data in real quick. You want 3 different columns. Okay, so then we're going to go up here to this top left corner. I'm sorry, not all the way over there. Not StatDisk, not analysis. Right now we just have data. So we're just going to click data here, okay? And then we want to choose explore data with descriptive statistics. Okay, descriptive statistics is what's mentioned there. This is where we get any calculation based on the data. And then it asks us to explore data from which column. We're going to end up doing all 3, but for now, let's just do the first column. This is the Frozen 2 data. One thing I don't know if I've pointed out here yet is that you can always click this Show Sample Editor up here to make sure you're choosing the right column. I wanted the Frozen 2 data. That is indeed column 1. Okay, so let's look at our results. So it has lots of things here, right? It has a histogram, has a box plot, has all of this information. So this is kind of like when we did the 1 variable statistics calculation in our calculator, except there's even more. So let's get a little bit closer. Let's see, the sample size is 5, that's correct. The mean, that's one of the things we want. It's 15. All right, so let's go ahead and write that down. N1 is 5, we knew that. And then the sample mean for this first sample is 15. It's 0.000000, so I'm not even gonna mess with that. Notice this also does give you the median, and I don't think it says the mode, which is okay. I do want to point out that even though you can check the descriptive statistics this way, on the final exam, if it tells you to show your work, you will have to show the work for how to find the mean or how to find a median. Remember, to find the mean, we just add up all the values and divide it by n, the sample size. Median would be putting them all in order from least to greatest and finding the middle value. Okay, so then we scan down. We don't need the mid-range. We don't even know what RMS is. We're just going to ignore that. S2, the variance. That's what we want. Now, we usually look for the standard deviation, S, but this time we actually do want the variance, and you'll see why in a minute. So that looks like to be 104.5. All right, 104.5, very good. Okay, so now we're gonna do the same thing for the third sample. We're going to scroll back up here, and instead of selecting column 1, we're gonna select column 2. And then click evaluate. Notice over here where it says in the results explore data, it changed to column 2 now. Okay, so this says the mean is 28.4, sample size is 5, variance is 68.8. So 28.4 for the mean, variance is 68.8. Again, sample size is 5, mean is 28.4, and variance is 68.8. Okay, so finally we have to do that one more time for the third sample. Change it to 3 and then click evaluate. It says column 3. So sample size is 5, mean is 49, and variance is 72.5. All right, sample size is 5, mean is 49, and variance is 72.5. Very good. Okay, so this is one of the main reasons we're not actually going to do any of these calculations by hand, because they're super complicated, at least compared to anything we've done so far. The basics is that the test statistic F, right, this is not Z and it's not T, this is a whole new distribution F, which we're not even going to look at, but it is a different distribution. It's the variance between the samples compared to the variance within the samples. And I said compared to, but literally it does mean divide. So when we say variance between samples, we're really calculating this n times s squared times x bar divided by s squared divided by, times p. No, I shouldn't say that. It's not times p. It's the variance pooled. The notation is even kind of confusing. So let's go over that. The variance for x bar is the variance of the 3 sample means. So if I went back up to the data up here and I entered the sample means as a new column, so that would be 15, 28.4, and 49. Those were the sample means that I've now got a new column, column 4. Oh, I don't know what I just did, but I think we're good. Okay, so then I could change this to column 4 and click evaluate. And now I can see the sample variance is 156.52. Is that right? Yes, okay, 156.52. I think I have an error in my notes here, but that's okay. So, oh no, I see the problem. I did not enter the right data. I entered 40 instead of 49. Huh, okay, so let's go back up to that. It should be 15, 28.4, and 49. Let me make sure I get that right. 49. All right, let's try that again. That's what I was expecting. Okay, so the variance is 293.32, which if you notice, the value that we've plugged in here for this s squared sub x bar is 293.3, which is rounded, close enough. Okay, all right, so it also says in. Now notice these samples have to be of equal size. They are, so in is 5 for each of them, so we've plugged in 5. And then s squared sub p is the pooled variance, which basically means the average of our 3 variances. Whew, this is kind of a headache. So if we took each of these 3 values and now took their average, we would end up getting 81.86. I'm not even going to walk you through that calculation. It's not worth it. We divide or multiply and divide, and we get 17.91. So our test statistic would be this. And then in order to figure out the actual p-value based on that test statistic, right, this is the equivalent of like our z test statistic or our t test statistic in the past. We're going to determine if f value is significant or not by looking at the p-value. We have to calculate the degrees of freedom, and these are really kind of strange degrees of freedom. It's k minus 1 divided by k times n minus 1. So k is the number of samples, and n is the sample size. So we had 3 samples up here, 1, 2, 3 samples. And their sample size, again, it has to be equal, so n is the same every time, it's 5. So we plug in 3 for k and 5 for n. We end up getting 2 over 12, and we leave it that way. We want to see the numerator, we want to see the denominator, we do not reduce, okay? So then to find the p-value, we're going to use this TI-84 calculator function FCDF. It's similar to the normal CDF or the TCDF functions we've been using, and let the test statistic be the lower limit. It could go into why that is with the F distribution, but I just don't think it's worth it. Know that F will always be your lower limit. So you go to it by choosing second vars, which is the distribution key. Option 9 is FCDF. You have to hit enter. And then you input the lower F value as your test statistic, 17.91. The upper F value is going to be some large number like 100,000, something like that. The numerator, degrees of freedom, right? Notice I told you not to reduce, is 2. The denominator, degrees of freedom, is 12. So you end up with this command here. And then if we calculate that out, so I could do that really quickly in my calculator. Let's actually walk through it. We go to second distribution, and then the 9th one way down here is F. Oops, I guess my computer's or calculator's a little bit different. Mine is actually the 10th, so be careful, it's FCDF. That's what I really want. FCDF. My lower limit is that 17.91. My upper limit is something really large. Degrees of freedom from the numerator are 2. Degrees of freedom from the denominator are 12. Hit paste and enter. All right, I got 2.49 e to the negative 4th. Remember, that means move the decimal place to the left 4 times. So I'm going to move it once and then have to fill in 3 zeros. Okay, so my p-value here is 0.1232497. That is a really small value, regardless of what significance level I decided on, which actually I didn't decide on one up here, but regardless of which one I decided on, this is a significant difference because that is so small. It's going to be less than any significance level. Okay, so that is how you would calculate it by hand. That was exhausting. I'm sorry, one more thing. So the p-value, like I said, is 0.0002. Let's just round, okay? Is it less than or is it more than the significance level? It's definitely less than. Alpha equal to 0.05. So we would reject the null hypothesis and conclude that we do have convincing evidence that there is a difference between the mean ages of people watching those 3 movies. Remember, whenever we reject the null, then we conclude we have convincing evidence either for the alternative, this was the alternative, that there was a difference, or against the null. So instead, we could have said we have convincing evidence that there or that the mean ages of people watching those 3 movies are not equal, right? And really, different and not equal mean the same thing. Okay, so we could also use StatDisk, and I think this is much faster. So I'm going to walk you through this real quick. And I forgot to change these names. This should be mu sub Frozen 2, mu sub Avengers, and mu sub Knives Out. Okay. Again, our null hypothesis is that the means are all equal to each other. The alternative is that the means are not equal. So we're going to enter those 3 columns of data again in the sample editor and StatDisk. We've already done that, so we're good. Then we're going to click on analysis and select one-way analysis of variance. Okay, so from this screen, we're good. We're going to click on analysis. Come on, analysis. Oh, my screen's frozen. There we go. And then, what did I say? One-way analysis of variance. There it is. One-way analysis of variance. And then we see a screen like this, which is what I have shown here. So from this page, leave the significance level, and then check the boxes for the columns that contain the data we want. And that's 1, 2, and 3. So we're going to check those 3 boxes. All right, so 1, 2, and 3. We have data in 4, but it's not part of the movie data, so we're just ignoring it. And then we click evaluate. So we should get something just like this. Let's see. We do. Okay, so I'm going to use the one on my paper just so it doesn't kind of glare like my computer does. So there's a lot of information here too. It's a little bit overwhelming. This stuff at the top you could just ignore. We really want to know the test statistic. That's pretty darn close to what we got, right? I think we got 17.91. 17.89 is very close. That's good. We can ignore the critical F. We didn't use the critical value method. We only used the p-value method, so we're going to look at that. And our p-value is 0.0025. If we had rounded our p-value, that's what we could have gotten, 0.0025. All right, we did it correctly. So again, since the p-value equal to 0.00025 is less than alpha, we reject the null. We do have convincing evidence that not all 3 means are the same. Notice I phrased it that other way this time. Instead of saying that they are different, I said that they're not all the same, not the null. Okay, we reject the null. We have evidence against the null. Okay, so that is it for when your sample sizes are all the same. We can also do analysis of variance when the sample sizes are different. So that is the situation here, and I'm going to go over that in the next video.